Last Friday when we met, we talked about what I thought was maybe the most important scientific technological advancement in the last 150 years, and that was you could use magnets to convert electricity into motion. In other words, you could make a motor, which is really, really cool. And so people did this. Gosh, I can't remember the exact year, but people did this in the 1800s, and they were able to make wires move, and they were able to attach it to stuff and make stuff move with electricity, which is really, really cool. And it's the basis for, you know, modern, well, it's the basis for motors, which are used in everything. But then, some people were just kind of wondering. They were wondering. And there's this guy by the name of Henry in the United States, last name Henry in the United States, and a guy by the name of Michael Faraday in England, and actually a whole bunch more people than that looking at this problem. Is it possible? We know, they knew they could go from electricity and create motion with it. Is it possible to go back the other way?
Yes.
Shall I say that again?
Yes.
Is it possible to start with motion using magnets and create electricity?
Yes.
How?
Ultimately, if you move a magnet to a coil.
So here's what we have. This is a galvanometer, and you guys know what a galvanometers do?
Right.
It's just a.
Electric.
Oh gosh, do you know how it's built?
There's
Shall we talk very briefly how it's built?
There's a coil inside.
Yeah, there's a coil inside. It's just a coil on a pivot. So a galvanometer is a device that's used to measure how much current is flowing. But it works basically like this. And everybody, you're going to have to pull out your right hand. So everybody pull out your right hand real quick. All right, so.
The metal.
All right, so here we go. What I have is a coil of wire oriented like this. Got it?
Yeah.
All right. Now this coil of wire is actually sitting in this magnetic field between a north and a south magnet, or north south pole and south. What way is the magnetic field point in this case? Do I have it up on the screen?
Right.
Oh, I don't have it up. Which way is the magnetic field point?
To the right.
To the right. Wait. To the right, yeah. From north to south. Okay, everybody using the right-hand rule, tell me what's going to happen to this coil of wire when there's current in it, Natalia. What's going to happen? So, current's going to go to the right along the front of the wire, of the loop, and to the left along the back of the loop. And then, so it's going to go, the right side, the current's going to be flowing into the board, and the left side, the current's going to be flowing out of the board. What happens to the loop?
Nothing.
What happens to the loop?
It's going to want to flip out.
Tell me which way the loop gets pushed.
Oh, that's
Right hands, everybody, let's go. Okay, for starters, front side of the coil, what happens? This side, right here. What direction is the current flowing? To the right. What way is the magnetic field?
To the right.
To the right. What way does the front side of the wire get pushed?
Up.
what?
Down.
What?
Nowhere.
It doesn't.
Nowhere it does.
It doesn't. Right, it doesn't. Because why?
Because they're in the same direction. The
Charges are moving in the same direction of the field. What about the back side of the wire? Does it get pushed? Doesn't get pushed. Okay. What about the left side of the wire?
Wait, our left or your left?
Up. It gets pushed
This
up.
side.
Okay.
Up.
Alright, so current is flowing out of the board. The field is
Why would you push?
to the right, so the left side of the
yeah,
wire
sorry,
gets
yeah.
pushed up. What about the right side of the wire?
No.
Down. And wouldn't you agree if there was no current, there would be no push?
Yeah.
And if there was lots of current, there'd be a lot of push?
Yeah.
And if current were going the other way, what would happen? It'd rotate the other direction. So you just put this little coil on a spring and attach a needle to it. Here's your needle. Here's your meter.
Sorry. It's got the poles label.
This, my friends, is called a galvanometer. Does that make sense?
Yeah.
All right. So depending on how much current is flowing through, it'll move either a lot or a little, and depending on the direction of the current, it'll move. The needle will either move left or right. Does that make sense? All right. So that's a galvanometer. So I've got a galvanometer right here, and a galvanometer, if you think about it fundamentally, is just a motor, right? Converts current into motion. So I got my galvanometer. The reason I like these things is they're super sensitive. They're way more sensitive, and you can see response on them way quicker than you can see on a digital multimeter. All right, so Justin has a challenge before him. I've got a galvanometer here. I've got some wires here.
Sorry, dude.
I've got a magnet. And the task, Justin, is to set all of that up, play with it in such a way that you get the current to be measured. You create current with motion using a magnet and some wires. Go. So, good luck, guys. So, what you just saw was Justin successfully created. He created a device, guys. He created a device that was able to turn motion into current, and that is amazing. What does that mean we can do?
We can take mechanical. We can generate electricity.
We can generate electricity, right? If fundamentally you can take motion and make electricity out of it, what can you do? How can you harness this ability?
By using anything that moves.
Anything that moves. What's an example of something that moves?
A person running on a hamster wheel.
Water, right. You can make a big spinny thing.
A person running on a hamster wheel.
A person's running on a hamster wheel. Hook that up and make electricity. What else can you do? You can use wind thingies, those with the big blades on top of the building that go nowhere. Right. What else?
Light. That's not the same thing.
No, a light bulb is fundamentally different. All right, yeah, so anyway, this invention is commonly credited to Faraday, but there was also an American who discovered the same basic setup at about the same basic time by the name of Henry.
Hey, is that a job, by the way? Can I run a hamster wheel and make money?
Yes, you could run a hamster wheel and make money.
How? Still working in the power.
You would sell it.
Oh, I would sell my electricity.
You'd sell all your effort as electricity to the power company.
About 7 cents.
Yes. And meanwhile, the amount of food you would be consuming to produce that electricity would be way more than the money they would pay.
But I would be in shape.
You would be in shape.
And making money at the same time.
Right. They actually, I was just listening to the radio yesterday or Friday on the way home. They were talking about a startup company that powers all your phone and your watch and your whatever else you have with your clothing from your motion. So yeah, I mean, basic idea.
Like that too.
Yeah. Well, the backpack that I've seen is just a solar pack.
Oh no! They have like a backpack that bounces.
That bounces and turns that motion into electricity. Yeah. So yeah, this is a really. If you think about the ramifications of what this means, you can take any motion and turn it into electricity. So think of how much time we spend moving, all the wasted movements we have. We potentially have the ability to capture a lot of electricity back, certainly enough to power our cell phone. Why should we ever have to plug our cell phone into the wall unless we're just sitting there, right? If you're moving all day, you should be able to power your cell phone or recharge your cell phone when you're not using it based on the fact that you're walking. All right? And there's been a lot of attempts to do this over the years. And it's something I thought a lot about when I was in college, when I was first learning this stuff. So anyway, here we go. Here's Faraday's basic setup. What Faraday realized, among other things, is that coil is actually a magnet, right? That coil right there is a magnet. Now, the permanent magnet is a magnet. When you move two magnets together, something happens. Well, Faraday didn't think of the coil as a magnet. He thought of it as a magnetic field capturing device. Kind of like a hoop. Where's my hoop? Here's my hula hoop. This coil, a wire, is a magnetic field capturing device. And one of the things he did is he realized that the closer the magnet, the permanent magnet is to the coil, the more magnetic field lines that were getting captured. In other words, the more magnetic flux was getting captured, right? So if he wiggled out here, he would get less current flow, and if he wiggled right here, he would get more current flow. Does that make sense? Why? Because it was capturing more of the magnetic field because it was closer. All right. Magnetic flux. We talked about this last year. BA cosine theta. You guys remember that? Well, something times cosine theta means what? It means dot product. So it's technically supposed to be a dot product. So the magnetic flux is defined to be in this class around the B dot dA integrated around the whole loop, which is why the little circle is around the integral sign. All right? And then you calculate it with BA cosine theta. So just like last year, there's the basic picture. If you've got a loop and you've got a magnetic field, the angle is defined to be the angle in between the magnetic field and the normal line to the loop. Everybody got that? So angle in between the normal line of the loop. Well, what's the normal line of the loop? What direction is the normal line to this loop facing right now with this hula hoop? Either front of the room or back of the room, right? All right. What about right now? Left side of the room or right side of the room? What about now? Up or down? Good? All right.
Bunch of monkeys.
Yeah. All right. Now, what that means is, let's say there was a magnetic field in this room facing north, because there actually is. If I hold the loop like this, what's theta? 90 degrees. So there's no flux going through the loop. And the other way to think about that is, well, the field lines are going that way, and I'm looking at it head on. None of the field lines are actually passing through the loop. Good?
Yep.
And the math is it's cosine of 90 degrees. All right. All right. Flux is field strength times area. So it would have units of Tesla for field strength and meters squared for area. So a Tesla times a meter squared is called a Weber, like the grill, or Weber, or Weber. I'm not sure. Got it? So if you ever see WB, that's what it is. It's one of those weird units that you almost never use, unless you're in a physics class. What's that? Not Wombo? No. All right, next. Faraday's law of induction. So, Faraday found that EMS was induced. Oh, guys, do you know what EMF is?
Voltage.
Voltage. It stands for electromotive force. He thought of it as a force that pushes charges. We think of it as a voltage difference or potential difference. Yeah. Was induced only when the magnet was moved either toward or away from the coil, but not when the magnet was stationary. This was the big idea. And Justin, like right off the bat, got that. You're not going to get anything out of the galvanometer if you're not wiggling the magnet. Right? From this, he concluded that the key was that by moving the magnet closer, more and more field lines pass through the coil. Should I say that again? When I take this magnet and I move it closer to the coil, more and more of the field lines from the magnet are being captured in this little circle. Therefore, the flux is increasing. And when the flux increases, you get a current flow. And likewise, when you pull it out, the flux is decreasing. You also get a current flow. When do you get no current flow?
When it's stationary.
When the flux is not changing. That's the key. Current will only flow when the flux is changing. All right. So here's Faraday's law of magnetic induction. He says that the EMF, or the voltage induced, is equal to, or depends on, how quickly the flux is changing. That's d phi over dt. All right? Then he's got an n. What's that n stand for?
Number of loops.
So what's n for this particular solenoid? 440. All right? So this is a 440 coil solenoid. So n would be 440. What's the negative sign? Do you guys know this? What's that mean? Oh, no. The negative sign is something way more complicated. The negative sign is a reminder. It means nothing other than remember to use Lenz's Law. Do you guys remember Lenz's Law? Okay. Suvi does, because she just saw it. Right. All right, and this is the rest of the day we're going to be talking about Lenz's Law. Faraday's Law is really easy. Lenz's Law is going to blow your mind. Yes?
So say we had like 440 loops the size
Of this, yeah?
this.
It'd be big.
Yeah, and we put a magnet through it. Would it produce the same amount of flux?
Yeah, that's a really good question.
That's like
If you had loops this big, 440 of them, would it produce the same EMF as that particular solenoid? Yes or no? Would it produce the same, more, or less EMF than that one if it had 440 loops? So 1 meter diameter loops versus 2 centimeter diameter loops. Which produces more EMF?
The same.
The bigger one. Why?
Because it's dot DA, so it's cross section.
Yeah, it's got more capability to grab flux, right? To grab field lines. So the bigger loops should produce more. Now, it's not a linear thing because the field lines, once they leave that permanent magnet, spread out. And so if you have, there's a point of diminishing returns, right? But in theory, the more of those field lines you can capture with your loop, the stronger the rate of change of flux will be. All right, so let's do Lenz's Law real quick. So here it is. Lenz's Law. Faraday's Law. EMF equals negative n over d times d phi over dt. This Faraday's Law includes a negative sign. This exists as a reminder that you have to figure out which direction the current's going to travel in the loop. All right? That's what the negative sign, it's a reminder that somehow you're going to have to use the right-hand rule or something to figure out which way current goes in the loop. So, here we go. I've got a little cheat sheet for you. If the change in flux is positive, then the induced current's flux is negative. What? Let's do this again. Let's do this in the middle of the room. Everybody, field trip to the middle of the room. Field trip to the middle of the room. All right, so once again, we are going to live in the pretend world, and we're going to pretend that the middle of this floor where it's painted blue is where all the field exists. And moreover, the field is coming down like rain from the sky, but only in the blue area. Got it? Now, if I were to put my wire loop in that field, and the field were constant, is the flux constant? Is the flux constant not changing? Yes, it's constant. So would any current be induced in that wire loop right now? No. But if the field over time were getting stronger and stronger and stronger, would the flux through the wire loop be changing?
Yes.
Yes, what would it be doing? It would be getting more and more, right? Okay, so let's figure out if the flux is changing through this loop, there should be a current induced, right? Let's figure out which way it is. All right. So here's the deal. That loop will have a current induced in it. Agree? And that current induced will tend to fight the change in flux. Shall I say that again? The current induced in the loop is going to resist the change in flux. In other words, if the flux is increasing down through the middle of the loop, what's the induced current going to create? A magnetic field that's going to go up through the loop. Does that make sense? So what if this loop creates an induced field that goes up through the loop, which way is the current got to be?
Counterclockwise.
This way.
Let's see. Right hand, everybody pull out your right hand. Let's see it. Okay, so up through the loop, right?
Yeah.
Which way is it got to go through the loop? Which way is the current got to be? Counterclockwise. Does that make sense? All right. Counterclockwise. Like that.
Oh yeah.
Make sense? This is so good. All right. Okay, a different situation. Let's say the field is getting weaker. Field is getting weaker.
Yes.
Now, so what's the induced going to do?
It's gonna line up.
It's going to try to resist the change, right? So it's going to want to create a field that is down to like beef up to keep from losing flux. So down, right hand, it's got a current's got to go clockwise.
Yeah.
All right, good. All right, so those are the basic scenarios. Let's do a different one. Okay, so here we go. We're going to start the loop outside the field. And we're going to push the loop into the field.
Yes.
How will the flux change when you push the loop into the field? Will it increase or decrease?
Increase.
It'll increase because the flux will be a bigger and bigger area, right? So the flux is going to increase downwards. So this is going to fight it, right?
Yeah.
So what way will the induced field point?
Up.
Up. So what way will the induced current point? Counterclockwise, like that. Okay. Now, next one, next situation. If I pull this out of the field, what's happening to the flux? It's decreasing down. So the induced has to be pointing down. So the current has to be clockwise. All right, last one. Okay, this one is tricky. Okay, we're going to actually rotate the loop. All right, so here we go. So right now, I'm going to start it like this, and I'm going to rotate it this way. What's happening to the flux? Decreasing through the loop, down through the loop, right? Whoa, decreasing. So what way does the induced current need to be? It then needs to be down through the loop, so it needs to be that way. Right? Now once it gets to here and starts going this way, what's going to happen? It's going to increase this way, so the induced has to be that way, so like that. Right? Then when you get to here, it's going to decrease down.
So it'll reverse.
So it's got to go this way. So the direction of the current just reversed.
Wait, what?
What is last year?
I said it, but you pointed the same direction both times.
Oh.
Yeah.
No, because I'm looking at a different side of the flip.
Oh, okay. So wait, if you were to create an AC current, would you have to do that, or?
Yes, this creates an AC current through this loop. Yeah. By taking the loop and rotate it in the magnetic field, you're creating alternating current. Sinusoidal, no less. Alternating current. Alright? Sinusoidal alternating current by rotating the loop. It's like at a minimum here, it's, let's see, maximum.
maximum there because the field's going down. So you have the most area right there.
Yes, maximum.
Then there's a minimum right there.
Minimum there. Then maximum, then minimum. And that. Anyway, sinusoidal. And it's all in the notes. All the different scenarios are in the notes. They're the same notes from last year. I drew them. I like them. I didn't change them. So yeah, take a look at that. But this stuff is tricky, this Lenzs Law thing. And I think we're going to do more Lenzs Law demos tomorrow. But for now, I want you to give it a chance. Take about 10 minutes. Get started on your homework. Go.